Greetings, how are we doing? I can't believe this worked. There are people here. How are you guys? Are we well? I'm very well, thank you. We are just going to do some... I think quite a few people have physics tomorrow, but I'm impressed that this worked. And there are some people here, so good stuff. I tried to put in questions that people wanted from yesterday's lesson. So a bit of KP and KC. Hey Zeril, how you doing? We've got some electrode potential stuff, and I've got some recrystallization and some organic techniques. So a little bit of everything. Let's just see how we get on. Andy, greetings. How you doing? Okay, shall we get cracking? We all good? Make sure you got a calculator ready. Obviously no workbook. Hey Dreety, how are you? Let's go. Okay, so I didn't get to the... I would think I was waffling a bit yesterday. And if I do that, just say, sir, you're waffling. But how was it, Andy? So I thought about this before I went to bed. And I thought I wasn't happy with my explanation. So I thought about it and reflected and thought I'd actually go through it properly. Hey, Camilla, how are you? Hey, Kosi. So we've all seen this slide, hopefully, from the KC lessons way back in September, okay? So we know that the system's at equilibrium because the concentrations are constant, they're not changing, okay? So the gradient equals 0. Any questions about this? So we're going to look through it, high gradient. So we're going to look at this through the lens of concentration first, if that's okay. So the equilibrium concentrations are given by the yellow line being the concentration of A in this reaction where we have A plus B goes to C. So the blue line is representing the concentration of B and this pink line is representing the concentration of C. And what we can say from here is that the system is at dynamic equilibrium as the concentration of species is not equal to each other, but the concentration of species remains constant. Okay, for the concentration of species to remain constant, what has to happen, or what must be happening to the rate of the forward and reverse reactions? Yes, they're equal, absolutely. So, which rate is that line showing? Is that the rate of the forward or the reverse reaction? Where it's starting off high, but then the rate is slowing down. Is that the forward reaction or the reverse reaction? Yep. Oh, it's the forward reaction. So it has to be the forward reaction because the A and B are being depleted. Their concentrations are going down. So the rate is also going to go down as well. Absolutely what Nafisa said. So therefore, if we were doing the reverse reaction, well, the reverse reaction hasn't started at time 0, right? So the concentration of C builds up. And as the concentration of C builds up, then the reverse reaction rate increases. So this is the reverse. Okay, so where is dynamic equilibrium on this graph? Well, it's not there because forward and reverse reaction rates are not equal. But when they are equal, that is where dynamic equilibrium is. So it's there. So this is equilibrium. Absolutely. Good. Okay, so let's move on. Now, let's say, for sake of argument, I do this to A. In fact, what change am I making on the system to A? Yeah, absolutely. So, you know, back in like GCSE, we're increasing the concentration. Let's say I'm injecting some more A in, okay? Let's say I'm injecting more A. That's why the concentration of A has shot up, okay? So if I increase the concentration of A, what's going to happen at this point? What's going to happen to the concentration of A and what's going to happen to the concentration of B? B remains same. Hey, Nessa, no worries, all good. So B remains the same. I haven't changed the concentration of B. Okay, but these are reactants, right? And if these are reactants, well, suffice to say, the concentration of the reactants is going to go down because I'm adding more A is going to react with B. So A and B are going to go down. Does that make sense? Because they're reacting. So if A goes down, let's say it goes down to this level. And if A goes down, then B has to go down as well. Okay, so let's say that B goes down to this level. Okay, well, if A and B are reacting to make C, what's going to happen to the concentration of C? The fact that it's a product that's being produced, because we increase A manually here. So we're adding more A, but if we're adding more A, that means the concentration of A has gone up. Therefore, there's more A to react with B. So if A reacts, its concentration goes down, and B's concentration goes down as well because they're reactants. But C is my product, more of it's produced, so the concentration of C is going to go up. So I'll try and find pink to match it. So let's say C does this. Amji, does that make sense? Let's say it does something like that. Okay, and what we're going to do is we are going to look at 3 sections of this graph. So we're going to look first at that section. Then we're going to look at that section in the middle. Then we're going to look at that section in the end, okay? So at this point in time, so this region here, what I want us to do is calculate Kc. So what is Kc equal to at that section? Reading off the graph, because Kc is equal to the concentration of C all over the concentration of A raised to the power of 2 times the concentration of B. So what is the numerical value at this point, up to like time 15? Well, C has a value of what? 8. A has a value of 2, but remember I need to square it. And B has a concentration of 6. Okay, cool. Yeah, absolutely. So it's 8 over 24, which is equal to 1/3. Does everybody agree? So in this section, we're saying that K isn't constant and it has a value of 1 over 3. Everybody happy with that? Categorically, that is true. Now, after we've injected more A in this section, does my value of Kc equal 1/3 or does it not equal 1/3? Have a look. It does not equal 1/3. In fact, what would we say we've done to Kc by increasing A? What have we literally done? Have we made the numerator bigger initially or the denominator? Yeah, absolutely. So initially, we are going to say in this region, so in this sort of section here, that slither, if we can see it, that initially Kc decreases as the denominator gets bigger. Why does the denominator get bigger? Because we added A. We increased the concentration of A. Does everybody see that? And I will link it to yesterday's question, trust me. So Kc is not equal to 1/3. And not only that, what's happening to Kc? Is it constant throughout? No, the system isn't at equilibrium. Why isn't the system at equilibrium? Because the concentrations are doing what? They're not constant. So if they're not constant, they are changing. Absolutely, good. So in this region, we're going to say that the system not at equilibrium as the concentrations are changing. But we know that the concentration has no effect on K. So if the denominator of K is too big, what's going to happen? More reactant is going to convert into what? To make the numerator bigger. More reactant is going to convert into product to make the numerator bigger. Absolutely good. So let's write this down in words. As K not affected by concentration, then numerator must get larger as more product formed to restore Kc back to its original ratio of what? Of 1/3. But let's see if this is true. Amji, I'm happy to do this next week as well, okay? Anything that will help. So now what we're going to do is we're going to have a look at this section here. So let's have a look at this section here. Let's see if we made more product, i.e. let's see if we made the numerator bigger and the denominator smaller. So what we're going to do is recalculate Kc with these new values. So what was my value of C? We'll read it off the graph. My value of C is 12. My value of A is 3, but I've got to square it. And my value of B is 4. Yep. So that's equal to 12. 9 times 4 is what? 36. So 12 over 36. Does that equal 1/3? So, have we restored K? Yes, we have. And have I explained it in terms of K? Yes, I have. So it kind of makes sense. Charlie, is that making a little bit more sense compared to yesterday? I hope it does. And everyone, I hope this makes sense. Wicked. Okay, so I thought we'd have a look at the increasing pressure in this way as well, because the example I gave yesterday was rubbish, and I was beside myself for giving you a rubbish example, but hopefully this fixes it. So, ignore these concentrations for now, okay? Ignore these concentrations for now. But what's going to happen to my concentrations if I increase the pressure? What happens to all of the concentrations or the pressure, if you want to look at it like that? They all increase, absolutely. And that's a feature of one of these graphs. If you increase the pressure, all the concentrations increase. If you decrease the pressure, all the concentrations decrease. So let's say, watch carefully because I haven't given you the values, so don't use these, okay? In fact, you can use these actually, but look what happens. So when we increase the pressure, A increases up to 4. B increases up to 12, so it does something like this. And then C increases up to 16. So it does something like this. Slightly off the charts. Okay. So then what happens next? So here I'm just going to say that we increase the pressure. So now the system is not at equilibrium anymore. Okay, so let's have a look at this in terms of K. So it was at equilibrium up to there. But let's have a look at what's happening in this section when we increase the pressure. So after we increase the pressure, if we look at this in terms of Kp, we'll just look at it through the concentration, it doesn't really matter. What's going to be bigger? Is it going to be the numerator or the denominator? Absolutely. So, what we're saying is Kp decreases initially as the numerator larger than denominator. Okay, well, we can't have that. So, how does the system respond? What does it do? Zero, go on. That should say denominator. That was just the wrong way around. As denominator, I know that's what you're going to point out. Larger than numerator. My bad. Yep, it was the wrong way around. Yeah. Thank you. It does shift equilibrium, but let's have a look. So what's going to happen in terms of A and B with the concentration or pressure? Is it going to increase or decrease if they react more? Yeah, so A and B, the reactants are going to decrease because it's going to shift to the side with fewest gas molecules, i.e. from left to right. So look what happens to the concentration of A and B. So let's say A does this. Okay, and let's say B does this. It goes from something to like... Okay, let's see if this works out better than yesterday. I'm hoping it does. Okay, so my A and B have decreased. Okay, so what's going to happen to my C if A and B are reacting to make C? We're making more C, so what's going to happen to the concentration of C? Yeah, it's going to increase. Now, it's off the charts, but let's say it does something like this. I'm making this up, by the way. Okay, let's say that settled at 21. I'm just making that number up, okay? So what we're going to do is we're going to figure out what Kc is back when it settles down. So once the concentrations remain constant, let's recalculate Kc. Okay, let's see if this works. So we're saying that C is 21. Oh, look who's here. What's up? I'm very well. How are you? Are you well? So A is what? 3 squared? Times the concentration of B, which is 7. Okay, so what does this give us? 9 sevens are 63. So what's 21 over 63? It is definitely 1/3. So do we get what we started with? Yeah, it's a better example. It's a better example for sure. Now, let's explain the second point. Let's explain the second point, okay? So how do we get that? What happens to the denominator? So Kp is restored as more product formed. So the numerator gets larger and the denominator gets smaller. Amaji, I spent some time thinking about these values today, really, but I mean, if you had a question, they'd also be thought as, they'd give you values that will work. But does the logic make sense in terms of Kp? Basically, so if they give you a question like this, rationalize it in terms of the numerator and the denominator changing. Is everybody happy with that? And the third marking point, I guess, was coming from that you had to say that the equilibrium shifts to the right. Done. Wicked. So, good question. So actually, Amji, on the mark scheme for yesterday's question, it would have allowed you to talk about concentration instead of pressure. It said in the allow section, allow throughout. So really, Kc and Kp can be thought of as analogous, but Kp is strictly related to species in the gas phase. So if you've got species in the gas phase, then we should be using the equilibrium constant for pressure, and not the concentration, strictly speaking. Pretty much they're interchangeable with a wordy question like this, but for a mathematical question, Kc we have to use square brackets, but for Kp we use partial pressures and curly brackets, or parentheses, sorry. Yeah, so just be aware that there is a difference in terms of the mathematical notation that we use. Cool. Let's go. Let's actually do this question. So we got to write the expression for the equilibrium constant Kc. So Kc is equal to nitrogen dioxide squared all over NO squared multiplied by O2. Now, technically, I'm going to put my state symbol in as well, because why not? Okay, what would happen if I used parentheses or curly brackets here? Hey, Mimi. What would happen if I used curly brackets? Would I get the marks? No marks. Exactly. No, Ambergy, you probably wouldn't. It's only one mark here. And then the other mark is to state the units of Kc. Okay, well, my units are going to be moles per decimeter squared in the numerator multiplied by moles per decimeter cubed square in the denominator multiplied by moles per decimeter cubed. So, Mimi, there is no booklet. We're just doing this sort of optional today. So, my units are 1 over moles per decimeter cubed, which is equal to mole to the minus 1 dm plus 3, and done. Any questions? Are we good? So that's your 2 marks. 1 for the expression and 1 for the units. Cool. Okay, by the way, if you think you don't even have the March module for maths, interesting. By the way, if you know anybody who would find this useful and they want to lock in, share the link, I suppose. If they're serious, obviously. If they just want to do business revision, then this isn't the correct place. So let's have a look at this question. I think this was a 5 marker, if I'm not mistaken. And it's actually a great 5 marker. So we've got to calculate the number of moles of nitrogen we don't even have to do an ice table. Wow, did you just say you're defo gatekeeping? Wow. We don't need ice, we don't need spice, and we don't need mice. Now, the reason for this is if we read the question, it tells me what the total volume is of the container. It's 4 litres. The system will reach their competition. Wow. Hunger Games. When did it become Hunger Games? Right. Yeah, it's normally rice. Thank you, Sky. I don't know what everyone's on about. Okay. So at equilibrium, the mixture contains... So it tells me what the equilibrium mixture contains in terms of moles, right? Thank you, Zuriel. Sharing the chemistry goodness. So we also know Kc. So we know what Kc is. So I've got to calculate the number of moles of nitrogen dioxide in the equilibrium mixture. Hello, Zuriel's friend, by the way. So let's go. So what I'm going to do, can't remember what Kc was. I'm just going to rewrite it, okay? So it's NO2 squared all over NO squared multiplied by the concentration of O2. Okay. Hi, Camilla. So, oh, you commented on the videos. Thank you. So, where do we go next? Let's think about what we know. I know Kc. I know what my moles of NO is, and I'll highlight that. And I also know what O2 is. Okay, so therefore, what is my unknown? Whatever you're left with, that's the variable that you have to solve for. And don't worry, you won't have a quadratic. Saint Maths. So let's rearrange for moles of NO2. Okay, so what we're going to do is multiply both sides by the denominator on the right-hand side. So this becomes Kc multiplied by the concentration of NO squared multiplied by the concentration of O2, which is equal to NO2 squared. You can, back in the day, used to get quadratics in chem for questions like this. Normally, one of the solutions would be on physical. Now, before we move on, where do we go next? I'm not even going to put any numbers in. Ooh, quadratics. Can't beat a bit of completing the square. So where do I go? Let's just do what to both sides. Okay, before I even do that though, because it's not asking me to find the, it's asking me to find the concentration, true, but I've got the concentration squared, so how do I unsquare it? Yeah, take square roots, absolutely. So if I square root both sides, I get this. Yep, and then what can I do to this term? Just as I'm looking at it, I'm thinking, I'll just take that on the outside, I'll do this. You don't have to do it like this, but if you want to, that's absolutely fine. Is everybody happy with that? And that's going to give me the concentration of NO2. Yep, so we've got the moles. I'm going to substitute that in and put that as a concentration in the equation. Absolutely. So let's go. I know what Kc is. Kc is 45. My moles of O2 is 0.8, but I need the concentration, so I'm going to divide this all by 4. And what I'm going to do is square root all of that. Then I'm going to multiply by the concentration of NO. I know the number of moles, so I'm going to do 0.4 over 4. And that's going to get me my concentration of NO2. Okay, so fire away in the chat. What do we get? Sky, check that. I think there might be a calculator error because it looks... Yeah. So, 0.3, but what are my units? Are they moles or are they moles per decimeter cubed? Look at what I literally calculated. Yep, I calculated concentration, so it's moles per decimeter cubed. So I need to calculate the number of moles of NO2. So remember, N equals C times V. Yeah, but I calculate error in terms of input. So therefore, what do I do? To get the number of moles, I've got the concentration, multiply it by 4, so it should be 1.2 mole. Sky Casey, do you see how we've done that? Is everything good? Let me know if that's all cool. Cool. As long as you guys know where you're making mistakes, that's the main thing. Okay, cool. Let's go. Okay, we didn't do this question yesterday, so let's do this question. Based on the data in the table, determine whether the forward reaction is exothermic or endothermic. Justify your response using the values of Kp. Masood, we're just going to do random chemistry questions. Let's go. So the way I'm thinking about this, the temperature is increasing. We're increasing the temperature, but Kp is what? Yeah, absolutely. So Kp is decreasing. And the only way that Kp can be decreasing is because of what? What must we be making more of? Are we making more product or more reactant? Yeah, absolutely more reactants. Therefore larger denominator, hence less than 1. Okay, good. So what's the inference here? If we are making a larger concentration of a reactant by increasing the temperature, the reverse must be endo, so the forward reaction must be what? Exo. And how do we actually phrase this? So as T increases, Kp decreases. And what I'm going to do, I'm going to give more than they need here, okay? So therefore the concentration of reactants increases. I'm just going to put this down. So the denominator increases. So as Kp decreases, the forward reaction must be exothermic. And I think when you're structuring your response to this, do it as this happens, therefore that happens, so this is the result. So try and put as connectives in and structure that as logically as it is in your brain, if that makes sense. So I've done this. What's the effect? Kp's decreased. Okay, the only way that Kp can decrease is if I have more reactants, so a larger denominator. And I know that if I increase the temperature, it shifts in the endothermic reaction, making more of that, so the reverse must be endothermic. Do you see how we've sort of cause and effect at each thing? Hopefully that makes sense. And it may just be for 2 marks, but 2 marks that I can get if I just logically write out each cause and effect. Cool. We don't need to do this question again. Use the previous slide for those 3 marks. But I can't remember who it was who wanted some E-cell type stuff. So let's do some E-cell type stuff, and then we'll do a bit of organic. Okay. Right. Storage cells and fuels. Okay, so electrochemistry. The electrode potential for 5 different redox systems is provided. Okay, so you're welcome. Right. A student decides to build an electrochemical cell using redox systems 1 and 4. Okay, cool. Sketch a fully labeled diagram showing how this electrochemical cell can be set up in the lab. Okay, cool. So before we even start, which is going to be my left-hand cell? Which is going to be my right-hand cell? Fire away in the chat. Yeah, we need a voltmeter. True. Let's go through it. Which one's going to be my left? Which one's going to be my right? Yep, absolutely. The more negative system is my left-hand electrode, and my more positive one is my right-hand system. Absolutely. Cool. All right, so now what we're going to do is not have a dashed line because it's going to leak out of that solution, or that vessel, sorry. Okay, so my left-hand cell, what am I going to have in there? Because the more negative the electrode potential, the more reducing that species is, or the more likely it is to be oxidized. So what that means is this is going to shift left and be oxidized. Yep, absolutely, the chromium. So we've got the chromium electrode in here, so we can have a solid lump of chromium. It's a transition element. So what I'm going to do is put chromium solid. That's one of my electrodes. Okay, so before I look at all the other stuff, let's do it logically. What am I going to have chromium in a solution of? What's going to be in this solution? Yep, chromium 3+, absolutely, aqueous. And what am I going to tell the examiner at this point? Yeah, I'm going to tell them the concentration. So this has to be 1 mole per decimeter cubed. Absolutely, good. And then what I do is I do the same thing for the other side, but it's going to be a slightly different. So more negative means more reducing, a better reducing agent, i.e. more likely to be oxidized. Treaty, if that makes sense. Okay, so Okay, so let's change this a little bit. So what is my electrode this time? Yep, loads of people have said it's going to be a platinum electrode. Absolutely. So there's a catalyst and it's a surface for the electrons to gather on. Cool. So what's going to be in my solution? Because I haven't got a solid lump there, because what's happening is this side is being reduced. So what's my solution made up of? You have to state all of the species, and I think it's actually 4. Yep, absolutely. So I need my manganate ion. I need my H plus ion. And I need my Mn2 plus ion. Good. You can include the water. I just don't think you needed to include the water because we're putting the state symbols here as well. It's sort of implied. Why is it made up of 3 species? Tell me what you mean. So Chloe, we normally put the most negative species on the left by convention and the more positive species on the right, because the more negative one gets oxidized and the more positive one gets reduced. So in the solution, we have to contain all of the species that are dissolved. So all of my ions should be included. The reactant side and the product side should all be included. And remember that it has to be, all of these have to have a concentration of 1 mole per decimeter cubed. Is that okay? So the main thing here is realizing that all of these guys, all of my ions have to be included. So all my aqueous species, include them and make sure that the concentration of 1 mole per decimeter cubed for each one. Okay, so we need to connect them up. So we need a wire connecting the left-hand side to the right-hand side. Okay, and then what's in between? So we've got a high resistance voltmeter in between measuring the voltage. Now, I'm going to put high resistance voltmeter, but there's one thing missing from my diagram, because it's actually not a complete circuit at the moment. Yeah, Kyosi, so it's normally like sulfuric acid or something like that. Yeah, so salt bridge as well. So let's add the salt bridge. And they shouldn't interact. So you normally choose an acid which has an anion which won't interact with the oxidizing agent, if that makes sense. I mean, I can't remember. You might have got the marks if it was the other way around. I can't remember what the mark scheme was saying. But you've got KNO3 aqueous, and that's my salt bridge. And that completes the circuit as it allows the ions to flow. Yeah, Chloe, so all of these, that's going to be 1 mole per decimeter cubed. That's going to be 1 mole per decimeter cubed, and that's going to be 1 mole per decimeter cubed. So they all have the same concentration. Camilla, no, you do need to know, though, that a salt bridge is made up of ions that flow through the circuit. Cool. A follow-up question. Let's say the voltmeter wasn't there and there was current flow. Equal number of moles mg, that's all it means. But we have equal concentrations, not equimolar, but equal concentrations of each species of ion that we have. Okay, so let's say the voltmeter wasn't there. If the voltmeter wasn't there, which way would the current flow? Would it go from the chromium to the platinum or the platinum to the chromium? Yep, left to right, absolutely. So the current flow would be in this direction. Why? Because what's happening to the chromium? The chromium is more likely to be oxidized. So the 3 electrons, I know it's not 3 electrons, so if anybody does physics here, don't get on my case. But the electrons that we lose in the oxidation reaction go in this direction, and then what do they combine with? They combine with my manganate ions and my H plus ions to make more what? Mn2+. Yeah, that's it. Do you see how it kind of works? So if we let this reaction continue, what would happen to my lump of chromium metal? Would it get bigger or smaller? The fact that we're losing electrons from them forming ions of it. Yeah, absolutely. So the left-hand side would get smaller. So if we remove the voltmeter, this side would get smaller. Cool. How do we feel about this question? Fire away in the chat. Let me know if it's okay. And the level of difficulty is like, you're thinking, you see this and you think, yeah, calm. Did I just say calm? I don't normally use that. Lovely. Cool. Okay, we've done that. Very calm. Nice. So, all right, this question comes up quite a lot. Just imagine are we in London? If we are, this is, it doesn't matter actually, this is a low traffic neighborhood. What do I mean by a low traffic neighborhood? These are bollards and your electrons are the cars. So what do bollards do to the electrons or the cars? They stop the car going through a road. This is a road, the wire, but this bollard stops your car going down that path and says, nah, you're not coming through. And that means we don't get any current flow. That means we get a more accurate measure of the difference in potential of one side and the other side. Hence, we're measuring the potential difference. So potential energy here and the chemical potential energy on the other side, or chemical potential, I should say. Okay, no, well, never say no. What does the fact that this is such a positive value mean? Tell you what, I'm going to quickly draw some rubbish sketches. So this is one equilibrium system. And this is another equilibrium system. Tell me which ones they are. So which one's chromium and which one's the manganese one? Oh, these are negative charges, so these are representing electrons. Which side has the more or which side is more negative, and which side therefore is representing the chromium and which side is representing the manganese one? Yeah, absolutely, because we're not saying there are no electrons, but it's an equilibrium process, right? So there may be some, but relative to what? Relative to what are we comparing this to get this value? Relative to the hydrogen electrode, we are saying that compared to the hydrogen electrode, this system of manganate and Mn2+ is more likely to be reduced relative to hydrogen. And for the chromium relative to hydrogen, we do, but it was just a rubbish drawing, MG. Don't worry too much about that. So relative to hydrogen, what can we say about the chromium system? So relative to hydrogen, the chromium system is way more negative, and that means it's more likely to do what compared to the hydrogen electrode? More likely to give out electrons. Yeah, or oxidize, absolutely. Okay, so follow-up question, which is more understanding type question. If I was to ask you to draw, yeah, better reducing agent. So if I was to ask you to draw a rubbish picture of the standard hydrogen electrode where we have H2 and 2H plus, what are my numbers of electrons for the hydrogen electrode going to be compared to the chromium one and the manganese one? Are we going to have more electrons compared to the manganese one or less? More than manganese, but less than chromium. Absolutely good. So something like that. I know it's a rubbish picture, but this is my 0 point. So this is more negative than my 0 point, and this is more positive than my 0 point. That's where those numbers come from. Remember, these are all equilibrium processes. Okay, so how do I know which is the more oxidizing and which is the more reducing? That's a good question, and that could come up. So team, help out. If something is more reducing, it gives out electrons. If something gives out electrons, that means it gets oxidized. So is that going to have a negative value or a positive value? No, negative value. So reducing agents have negative values because they give out what, Amberjeet? They give out electrons, and electrons are negative. But they themselves get oxidized because they give out electrons. So if something loses an electron, it's oxidation. So these will have more negative values. If something is oxidizing or an oxidizing agent, what does it do? It doesn't give out electrons, but it takes electrons. If it's taking electrons, it's getting rid of those electrons in a way. It's an absence of negative charge if you want to look at it that way. So if it's gaining electrons, it's being reduced itself, so therefore it's going to have what charge, relatively speaking? Not negative, but it's going to be more what? It's going to be more positive. Yeah, absolutely. Good. Because those electrons, those negative species, are being taken in by the thing on the left. Okay, everybody happy with that? Cool. Now this comes up over and over again, this type of reaction or type of question, where we've got to construct the overall equation for this reaction. Okay, we've done this quite a lot. You should be bored or sick to death of it. So we're looking at systems 1 and 4. Okay, so what am I going to say about system number 1? If it gets oxidized, what's the oxidation reaction going to be? Is it going to be Cr3 plus goes to Cr, or Cr goes to Cr3 plus? We flip it. Absolutely. Good. Yep, exactly. So it's Cr goes to? So therefore, yes, and we have to scale. Good. So my reduction reaction is MnO4 minus plus 8H plus 5 electrons goes to Mn2 plus 4H2O. Okay, there's a problem. So what's the lowest common multiple here of 3 and 5? Okay, so to get to 15 at the top, we multiply it by 5. And to get to 15 at the bottom, we multiply it by 3. Okay, good. So I'm just going to do that here in one hit. 5, 5, 15. Okay, so 3, 24, 15, 3, and is that 12? Yeah, props. Okay, so now all we're going to do is add these guys up. Cancel that out, cancel that out. So 5Cr plus 3MnO4 minus plus 24H plus goes to 5Cr3 plus 3Mn2 plus 12H2O, and the job is done. Hurrah, let's move on. Now it's only 1 or 2 marks, but it's not tricky 1 or 2 marks. If we know what we're doing, we've done this lots. So let's drill this skill and get the marks. Any questions? Are we good? Let me know if you're happy. Zuril, I think there's an alkali one coming up. There's an alkali one coming up, actually. Okay, wicked. Okay, so yeah, absolutely. The more negative one you flip, because what that's saying is, if that wants to give out electrons, it's not going to move in the reduction reaction. In fact, what's going to happen? If it's giving out electrons, it's being oxidized. So it's start with what you have and then go the opposite direction in which you generate electrons. So you flip that one. Yes, in short. Yep, Amji, that's one way of doing it. So E cell is E red minus E ox. You can do it that way. Amji, it does come up, but you know, it's going to be like 1 or 2 marks, but please practice it as well. Okay, let's have a look at question II. Using the electrode potentials and equilibrium principles, explain why MnO4 2- is able to disproportionate in acidic solution. Okay, it's a 2 marker, but if we understand, and I think we do, yeah, definitely. Does this feel quick today? It's 6:30 already. Feels quick. Why can the manganate 2 disproportionate? So, first of all, let's find where MnO4 2- is. Which redox system do we see MnO4 2-? Yes, absolutely. So we're going to use redox system 3 and 5. Absolutely. So, which system is going to be oxidized and which system is going to be reduced? We always think about it in oxidation and reduction terms. Fire away in the chat. Yep, absolutely. 3 is oxidized, so 3 goes in this direction. I'm not joking. If you annotate it like this, you will get the mark, okay? Just show the examiner that you've properly annotated it, though. So it says system 3 shifts left, i.e. is oxidized. You've shown that it shifts left. Or just put shifts left. And this one shifts. Right, that's 1 mark. That's it. Okay, but I want to do it properly. I'm going to maybe long it out a little bit, but for good reason. So, what's my oxidation reaction here? Do we all agree that my oxidation reaction is the MnO4 2- making MnO4- plus an electron? Are we happy with that? Yep, okay, cool. So then, what's my reduction reaction? It's system 5 just moving from left to right there, isn't it? So MnO4 2- plus 4H plus 2 electrons goes to MnO2 plus 2H2O. Okay, lovely. What's the problem with this disproportionation? What is wrong with my oxidation reaction? Because my reduction needs 2 electrons. Yeah, absolutely. So we scale by a factor of 2. This has to be equimolar. However many moles are given out in oxidation, the same number of moles need to be taken in for reduction, or vice versa. Okay, so now we're in business. So now we can just cancel out terms. So I cancel out my electrons, and then I look carefully. How many lots of MnO4 2- do I have? Yeah, I've got 3 lots of it. 1 here and 2 up there. So 3 in total. Plus 4H plus goes to 2 lots of MnO4- plus 2H2O. Don't worry about states here, Mimi. No, you don't really need to for this. Okay. You'd get 1 mark because you've kind of shown that shifts left and this shifts right. And you've also shown it here as well. That's what we're doing, okay? That's what we're doing in that green box. That doesn't give you an extra mark, but it helps us for the next bit. So where is the second mark coming from? You could try waffling. What is the next thing that I would probably logically do? Exactly. Work out E cell and show it's feasible. Okay, Charlie, that's actually the next question. So the explain is, for explain, we have to use the electrode potentials and equilibrium principles. So now let's work out E cell. I think I changed the order of the actual questions from the original. So E cell is going to be what? It's E red minus E ox. Do it if you like my way, do it my way. I'm just trying to keep it the same way that people are taught. So the reduction is plus 1.7. Absolutely, Andy. So plus 1.7 minus E ox, which is minus 0.56. So what do we get? So plus 1.14 volts. So feasible. That's it. Done. Wicked. Do it. Make sure you go through those lessons, Andy. Cool. So here is the other question where it says, using oxidation numbers, explain why this is an example of disproportionation. So I don't have to use electrode potentials for this reaction. It's what Charlie said. I just have to look at the changes in oxidation state. Okay, well, what's my oxidation state in MnO4 2- of the manganese? True, but I have to use oxidation numbers, Kyoshi, so I can't just say that statement. Yep, plus 6. In fact, it's plus 6 how many times? 3 times. I might just write that there to help me, okay? Camilla, because if it's positive, then feasible. The Y is... I'm sure you're going to get bored of this. So what do I need for delta G, for a reaction to be feasible? What does delta G need to be? Positive or negative? We know for a reaction to be feasible in terms of delta G, it has to be negative, okay? N is the numbers of electrons, so that's a positive value. This F is a constant, it's Faraday's constant, it's a positive value. So therefore, if E cell is a positive value and we're multiplying all of this by a negative, what's that going to give us? Positive times a positive times a positive, then times a negative. What's that going to give us? So basically a positive times a negative is going to make it negative overall. So therefore, feasible. Okay, but if E cell was negative, a negative times a negative would make a what? I'll do this one here. So that's minus, and if we multiply it by a negative, delta G would be positive overall. And if delta G is positive overall, this would be not feasible. Do you see the link to delta G here? That's why, really. Because, in effect, delta G is looking at the enthalpy and the entropy associated with the process. Cool. Okay, so going back to the oxidation states, what's my oxidation number in MnO4? Well, we know it's plus 7. We've got 2 lots of it, so it's plus 7 twice. And then what's my oxidation number in MnO2? Probably, Andy. Have a look. There was so many redox titrations in that and the homework, so it's definitely worth having a look. Not in MnO2, Driti, because... Fair enough. Have a look. Yeah, it's plus 4 because oxide is always minus 2. There's 2 of them, so we've got 4 negative charges. It's neutral overall, so therefore this has to be plus 4. Okay, so... let's have a look. Let's explain this in terms of oxidation states. So we go from plus 6 to plus 7. So if we go from plus 6 to plus 7, what's happened? Is that oxidation or reduction? Yep, absolutely. So 1 electron oxidation. Good. So then if we go from +6 to +4, that's a 2-electron reduction, right? So there's my reduction. Done. So one element is simultaneously oxidized and reduced, and that is manganese in MnO4 2-. You can add that bit in if you want to, but we've shown it with oxidation states. Not important to add that extra statement in. Cool. Thoughts? Let me know in the chat. Be honest. How are we feeling? Confident on electrochem and stuff? Let me know. Wicked. Good. Electrochem, once it clicks, it should be like 3 marks. But I think that initial barrier to entry is quite high. Well, here we go. Okay. Where's the Stein from? It's from something called the Oktoberfest. Have you heard of Oktoberfest? Yeah, like there's a high activation energy to understanding it. But once you understand it, you're rolling down the hill. Blood's talking like an economy. Is that a beer fest? It might be, Sky. It might be. So what's the difference between alkaline ones? Okay, let's have a look at an alkaline one. No comment. Don't know. I don't dye my hair, as you can see. They also have liter steins, liter mugs like this. That is ridiculous. Right. We've got to write the half equation that takes place at the negative electrode. This is a banging question, and I know it's only 1 mark, but it really shows understanding. I think they were blonde tips, Andy, if I'm being honest. Right. This one needs a bit of concentration for 1 mark, okay? So it tells me that redox system 2 from the table is used as the positive electrode. When we're reading this, what does that mean to us, chemically speaking? Is that the electrode that's being oxidized or being reduced? Exactly, that's the electrode that's being reduced, right? Good. So what that means is, which direction is redox system 2 moving in? Is it moving right to left or left to right? Look at where the electrons are. No, Andy, that was yeah. So right to left or left to right? What do we say? What's my favorite movie? I have lots. Yeah, left to right, and it depends on the mood, right? Yep, because that's being reduced. Good. I'll answer the movie question in a sec. I'll think of some good ones. Right, so what I'm going to do next, so I don't want the question to get the better of me, I'm going to look at the chemical equation, because I know if I take my 2 half equations for my oxidation and reduction, I can work out what the overall equation is. So I've got... Barbie, where did that come from? It's not bad anyway. Hang on, who's seen Barbie? It's not actually not bad. Why are you hating on Barbie for? If you've seen it, back me up here. Right, thank you. It's not great, but it's okay. There are worse movies. Ones that KBM has seen. Right. So what's happening is, my O2 is going to H2O. In fact, no. Where is my O2 going to? It's not going to H2O. Where is my O2 going to? I think it started off okay, then it wasn't great afterwards. Because it's not actually on the equation. OH minus, exactly. So look, my O2 is going to OH minus. Okay, so what I'm going to do is let's split this up into a reduction reaction, okay? So I've got O2 plus my 2H2O plus my 4 electrons going to 4 OH minus. So there's my reduction reaction. So basically the question is saying, what's my oxidation reaction? Okay, well, what's my oxidation reaction? So I've taken account my O2. So where's my H2? What's my H2 forming? My H2 must be forming what? Water, exactly. Okay, so okay, now how do we think about this? What's the next step? Because I know if I add my reduction and oxidation up, I get the overall equation, right? So what am I thinking? What do I need to add on the left-hand side of my oxidation reaction? Have a look what's on the... Oh, can't look, because for my reduction, I've got electrons on the left-hand side. Yeah, so my OH needs to cancel. Agreed? So I'm going to add 4 OH minus here. Okay, so if I add 4 OH minus here, and it's an oxidation reaction, by definition, what do I need on the right-hand side? Is it 2 electrons all, though? Check. It's 4 electrons. Okay. Now, how many waters do I need? It will make sense once we go through it. It's a good question. I'm going with Sky because you've got 4 hydrogens here and you've got 2 hydrogens here. Or maybe it's not, maybe something isn't right here. I don't know. What do we think? So if I really look up here, I've got 2 H2, so I need to account for that. So in total, I've got 4 hydrogens here and 4 hydrogens here. So I've got 8 on the left-hand side, so I definitely need 4 on the right-hand side. Now everything balances, okay? You could use multiples. Let's go with what's in the chemical equation given to us. Okay, now what can I cancel out? Let's cancel my electrons out. Let's cancel my hydroxides out. And let's cancel my waters. Can I cancel any waters? So I've got 2 here and 4 here. So that becomes 2. Okay, does that work? If I add them up, do I get 2H2 plus 1O2 makes 2H2O? Yeah. So the half equation that takes place at the negative electrode is what? It's this one. It's a tough one. I'm not going to lie. That is a tough one. But remember, how many marks is it worth? I'm not going to lie. That is a tough question. It's a 1-mark question. It's literally a 1-mark question. This is one of those that if you struggled a bit, you look at it and you think, I don't know it straight away. So what do? What you don't do... Hi, Cameron. So what you don't do is this. You could just remember it for 1 mark if you want. But what you don't do is spend 25 minutes on it. You don't get what? You don't get emotionally invested in a 1-mark question. You skip it if it's not obvious to you straight away. You star it and you come back. That's called exam technique. Does that make sense? Fair, but like if it's not obvious straight away, you come back, you spend a bit more time on it at the end once you've done everything you can do first. Okay, so the oxidation reaction is this. You could have halved this one. So if you halve it, you could have just said this. Or you could have used multiples. It's absolutely fine. So if we do that, you could have done that. or you could have used the one that we used. It doesn't matter, okay? But once we did it, does the logic make sense? It's actually, there's quite a nice beauty in it if you understand your redox and your oxidation reactions, right? You know that terms need to cancel out, and you can see how they all cancel out to give you this. And you linked it back to the actual equation you got. I think it's quite nice once it makes sense. Okay, what do we reckon the next question is going to be, even if I don't see it? I mean, I do know what it is. Okay, so I'll do it in a sec. I'll go back through it in the end, okay? Well, what don't we know about this oxidation reaction? Skip but come back, that's what you mean. So I know what the reduction potential is. The reduction potential is plus 0.40 volts. I know that. But do I know what the oxidation potential is? Exactly, E cell. It's going to be related, right? So it tells me that the total potential is 1.23 volts. Okay, so that's E cell. I know that E red is what? 0.4? So let's do it. E cell is equal to E red minus E ox. So I know these two terms. So I need to calculate what E ox is. So if I take E ox over to the other side, that becomes plus E ox. And this becomes what? E red minus E cell. Oh, check the signs, guys. Check the signs. Exactly. It's minus 0.83. Okay, so E ox is equal to plus 0.4 minus plus 1.23. So it's minus 0.83. Okay, what does that actually mean? Well, okay, but let's think like an electrochemist. So let's think in an odd way. What we're saying here is, we are saying that the oxidation reaction is this. Was it 2OH minus? And hang on. Let's go back. Let's have a look. What did we come up as the reaction? Okay, here it is. This bit's extra, by the way. So how are my electrode potentials usually quoted? They're quoted as reductions. So what we're saying is this: H2O plus, or put the 2's, not important. So what is my E value for that direction? Thank you, Andy. So for that reaction, as the reduction, it's minus 0.83. But what did we do? Remember, this is an equilibrium reaction. What are we doing? We are going in the opposite direction, so we're oxidizing it. So if we're oxidizing it, what is that value going to be? It's feasible in the way that we're flipping it. Yeah, so in the oxidation reaction, it's feasible. But, Amjad, you sure? So it's negative for left to right, but right to left, that's the oxidation potential, so that becomes 0.83. It's because these are always quoted as reduction potentials by convention. So the oxidation potential is plus 0.83 because we're flipping it. But the reduction potential has to be the negative value. Does that logic make sense? Electrochemists are a bit odd. So this is, if you do it this way, it's actually, this EOX is giving you the reduction potential. But if you do it my way, and I guess the way I think Charlie does it this way, it makes a bit more sense. But I don't want to confuse you doing it that way. Charlie, let me know if that way makes more sense. I think it does. Okay, because we're flipping it already and it makes more sense chemistry-wise. So the answer is this. That is the answer. This is extra to explain where the answer comes from. Is it, do you want to see my method? Exactly. So you flip the sign of the oxidation first because it makes more sense chemically. You're already doing the oxidation reaction. So in a way, you're getting the true value of the oxidation. Okay, cool. If anybody wants to see it, I'm happy to do it. If not, Andy, I did it both. So feel free to watch him. It will make sense. Show them the better way. Okay, cool. So if you do it my way, we know that E cell has what value? Okay, but this is going to be audience participation. Go for it. So that is plus 1.23 volts. Agreed? And what's E red? Well, I know that E red is given to me in the question. It's 0.4, plus 0.4. So therefore, EOX, true EOX, is going to be 1.23 take away 0.4, which equals plus 0.83 volts. Agreed? But this EOX is for what? We flipped this. So if we flipped it, the reduction potential, because we quote reduction potentials, the reduction potential is just going to be that value, but with the sign changed. Because this is for whatever it was. Yeah, I'm copying. I am getting old. So this is the value for the forward reaction. Okay? So that's the value for the forward reaction. I.e. the forward reaction is plus 0.83 volts, i.e. the oxidation reaction. But how are they normally quoted? They're normally quoted as reductions. So if they're normally quoted as reduction potentials, i.e. the reverse has to be Does that make sense? Which way do you prefer, the first way or the second way? I think the second way makes way more sense, chemically speaking. But let me know in the chat. 100%. 100% the second way. It just makes sense. Because if you split it into two processes, they make equal sense. Fair enough. I always used to teach it this way, but I've changed. Go to doc, please. What does that mean? Right. Okay, we've got about 10 minutes, and then I can't say later today. We're going to do a little bit of organic. I can't remember who it was. You're coughing. It's okay. Don't stress. Don't stress. Zuriel, fire away. What's up? Yep, go on. What's the doc going to say? It's just a cough. SP3 hybridization. I do know SP3 hybridization. Yep, fire away. Yep. Whilst we're waiting, you can do this question. when you excited the 2s electrons into the 2p orbitals? Yep. It is a catalyst, Damage, absolutely. Magnesium's, if you paid attention to group 2, magnesium's not very reactive in water. Yep, so Zero, we do this. So that's a normal configuration, and what we do is, let's say we take this one. It's okay. You weren't there for that lesson. But nice try. Can't believe you're trying to mug me off. Right. So. Then what we do is, now we have an s orbital and a p orbital. What we do is we literally combine all of these. And if we combine all of these, then we make... There's my s and there are my p orbitals, and I've got 3 of them. One here, and one here. So then when I combine these, I make sp 3 hybridized orbitals. Andy, check that. You sure? Because I've got one s orbital, not the electron in it. That's an s orbital. And I've got this p orbital, this p orbital, and this p orbital, and that's what the 3 means. And these can form 4 bonds exactly because I've got 4 unpaired electrons. This occurs in alkanes. So carbons with 4 bonds, as a model, it would be sp3 hybridized. But if we have carbon with 3 bonds, or double bonds, then it's going to be sp2 hybridized. Fair, Andy, I agree with that. And sp3 single bonds. Cool. Shall we leave it there and we can do some organic next week? It's entirely up to you, or we've got 8 minutes and we can do organic. Or Andy's got a question on lattice enthalpy. It's entirely up to you. We can do the last 6 minutes on recrystallization if you want. Your shout. Chloe, don't worry. You've probably got better things to do. Okay, let's go then. So... Okay. Covalent character. I'll try and quickly do covalent character, and then I'll try and do recrystallization. I swear we did covalent character. Camilla, that was catalyst. Okay. Remember, if you haven't seen... Okay. Yeah, you do. There's a 2-hour video or an hour video or something on Born Harbor cycles on the channel. Watch it. If you want to know about Born Harbor cycles. If you don't watch it, obviously. So let's say... I've got some Mg2 plus for sake of argument. And then let's say I've got, I don't know, F minus. Forget about the charges and the number of ions I need, okay? Just for a second. Now, what would you say about these ions, roughly speaking, in terms of size? Similar, different? What do we reckon? Not boiling points. Yeah, similar sizes, okay? Similar sizes. Now, we say that cations are polarizing. What do we mean by polarizing? Some people are polarizing. They can cause things to split in 2 different directions, right? If you want to think about it that way. In the chemistry context, it means that they can attract electron density in the anion towards themselves. Does that make sense? So anions are polarizable. What do we mean by polarizable? Wagwan Joseph. It actually makes it... Oh, Chloe, hold up. We're getting there. So anions are polarizable. Try and get away from the concept of electronegativity for just a second, okay? Because electronegativity's definition is the ability of an atom in a covalent bond to attract a shared pair of electrons. This isn't looking at covalent bonding. This is looking at ionic bonding, okay? I know there's a spectrum, and we'll look at that in just a second. But if anions are polarizable, that means their electron density can be distorted. Now, cations the smaller and more highly charged then these are more polarizing. And anions the bigger and more highly charged these are more polarizable. Okay, so let's have a look at, I don't know. Let's go for Mg2 plus again. I know the size has changed, but let's say I'm comparing now to iodide. What's the first thing that you notice about the iodide ion compared to the fluoride ion? It is a big ion. Iodide ions, my teacher used to call them fat and floppy. So if they are fat and floppy, what can you do to the electron density? Where is the electron density going to be attracted towards? I don't have any blue tack. Do I have blue tack? Let's see if I've got some blue tack. Yeah, floppy. If something's a bit floppy, it's like this, right? Don't make me dance. Right, let's see if I've got any blue tack. I don't know if I have. It's going to be attracted towards the Mg2 plus. No, I don't. Oh well. So what happens is this. Its electron density, because it's not very attracted to the positive nucleus, it's not highly held, it's going to be pulled towards this cation with a plus charge. Okay, if it's pulled towards the cation with a plus charge, look what happens. What was an ionic bond, strictly speaking, now becomes what? Where we have electron density overlap. This starts looking a little bit more what in comparison to the one at the top. So the electron density has been sucked over towards the Mg2 plus. What type of bonding is this starting to look like? Yeah, it's starting to look more covalent, right? More covalent than the magnesium fluoride. So if it's more covalent than the magnesium fluoride, we're saying that the magnesium fluoride is more what? If there's no sharing of electron density, because that's what a covalent bond is, right? It's sharing of an electron density or electron pair. So what's the magnesium fluoride going to be? Is that also going to be more covalent, or is it going to be the opposite of covalent, which we know what that is? Okay, but it's sharing of electron density, Chloe. So in a covalent bond, yeah, it's going to look more ionic. If this is H and this is H, this is what the electron density map of an H2 molecule kind of looks like. It looks a bit like a peanut. A monkey nut. Well, look, is this starting to look like the electron density map of a covalent molecule, more so than this one, where the electron density is localized on the ions? So here the electron density is localized because this is more purely ionic. But here the electron density, look, we're starting to get some overlap between the two centers. Does that make sense? Is it starting to click a bit? So that means if something is more ionic, this means that the Born-Haber cycle, which is an experimental value, will be in close agreement with the what? With the theoretical value, which is based on a calculation where my ions or my atoms are modeled as pure ions, as point charges. So what does that mean if they're modeled as pure ions? There's not going to be any sharing of electron density taken into my calculation, okay? So in my calculation, which is my theoretical value, it's purely based on my ions being spheres. But why is my calculation going to let me down for magnesium iodide? What is it not taking into account? It's not taking into account the fact that there is some degree of covalent character or electron sharing. Exactly. So we're going to finish on this because exactly, good. I would like somebody to find the lattice enthalpy for the Born-Haber value for magnesium iodide. I'm looking as well. What do we get? So, Andy, you're saying minus 1944 for the theoretical or the calculated. And the Born-Haber is what? So you're saying minus 2327. So is there a big difference between the two? That looks like quite a big difference to me. So then what we're going to do is we're going to finish up on, can somebody do the same thing for magnesium fluoride? Can you find the Born-Haber value, the theoretical, or the calculation as I'm going to call it, versus the experiment, which is the Born-Haber value? Minus 2957, minus 2913. Look, I didn't even know what those values were. Just based on our logic on this page, what can we say? That magnesium fluoride is mostly purely ionic, or way closer because it matches in agreement to our calculation, versus this one, because experimentally we get more energy out, because not only do we have ionic contributions, we also have what? In addition to ionic contributions, we also have we've got ionic contributions and covalent contributions. But the problem is, electron sharing. But the problem is, does the calculation take into account any of my covalent interactions? No, it doesn't. So this doesn't account for that. So that's why there's a big discrepancy between the two. Is that helpful? Okay, yep. So tell me, what does a so mean? Tell me what that means. Does it make it less exothermic? Always. Are you sure? Look at the values you just gave me. This is the experimental value. So this is taking into account the true nature of it. So this is ionic and covalent. Is that less exothermic or more exothermic? No. I said the calculation only assumed pure ionic. If you look here, the calculation, which is theoretical, doesn't account for covalency. So Born-Haber, which is an experimental value, takes into account all the interactions because it's from experiment. So covalent character means that there's more sharing of electron density, which is a way to describe covalency. Chloe, yeah, absolutely. Hi, GT. So if they're in agreement, if you have a good match between calculation, so calculation is only purely ionic, but the Born-Haber takes into account all interactions, if you want to think about it that way. What can we say if these guys are in close agreement? That there isn't much covalent character. Yeah, usually, Andy, that's the pattern, but there's just going to be a discrepancy between the two usually. But in normal cases, it might make it more exothermic in a way. But if there isn't a big difference between the two values, we can then assume that it's mostly ionic because we haven't got that large degree of covalent character. Does that make sense? Now what I'd recommend is go through and watch that Born-Haber video towards the end. If they ask why the experimental lattice enthalpy is different, you say the experimental lattice enthalpy takes into account covalent character, which the theoretical value doesn't. Because that's based on a model which is purely ionic. There is another way to think about it. In fact, I'm going to go through a covalent example if you want me to, if there's time. I know I'm running out of time. But I'm going to ask you a question, okay? Let's start thinking like chemists. So being simple-minded individuals. So what's the FF bond value? So like 154. Okay. So what is my HF bond value or my bond enthalpy? I think it's cool. The next bit is proper cool. As a mathematician, or the fact that we've done GCSE maths, what would... Try again, think about it differently. So what we're doing is we're taking one H and one F and we're just mashing the two up together. If the electron density is slap bang in the middle, which it should be for a covalent bond, what do we expect the bond enthalpy to be? Mathematically, what would be a good approximation here? So maybe 432 plus 154 over 2. Yeah, the mean, absolutely. So what do we get? 432 plus 154 over 2. Okay, so we're saying 293. No worries, that's good. Like, I get what you're meaning. So, if we actually look at the HF bond value, on my channel, Andy, it's called Born-Haber cycles. Everything you need to know about Born-Haber or something like that. So, the actual HF bond value is... Why is the HF bond value 565? Whereas, logically speaking, it should be around 293. Why? What is that telling you about the position of that covalent bond in this case? It's closer to F. Okay, it's not all the way at F, but it's closer to F than we'd expect. Because in a covalent bond, we normally expect it to be slap bang in the middle. Okay, what is the consequence of that? If something is pulled way over to F, we'd expect it to be what? DW, greetings. This is starting to look more what? Because this is a whopping great big negative charge now. And that's a whopping great big positive. So much so, it's starting to look less covalent and more what? Exactly, it's starting to look more ionic-like. Exactly, it's not fully ionic because the fluorine hasn't taken that electron all the way to pull itself. But it's got, in fact, now tell me, what are my two interactions here? Well, Chloe, why does it... Okay, I'm getting there. So, the fact that it's closer here. Imagine if HF was ionic. If HF was ionic, we'd have these two ions, right? But we don't have an ionic compound yet. We don't have one. But the fact that we must have a higher value means that, yeah, we've got a covalent interaction, but what other interaction are we starting to get more of? Not fully, but it's starting to look more like that. Starting to look more like this. Exactly. So it's starting to look a bit more ionic as well. So when your teachers told you, yeah, there's ionic bonding and covalent bonding, that was a lie. In fact, there is a what? There is a spectrum. So nothing is purely ionic and nothing is purely covalent. There is a bit of both. And this also accounts for the higher value that we see in HF, because not only are there covalent interactions, there are also ionic interactions. And in our calculation, which should make sense, why is our calculation lower than expected? What didn't our model in our calculation account for? Yeah, Chloe, if it's both, then it's going to be more exothermic or like a higher value, right? Absolutely, we didn't account for ionic interactions. Ionic character, absolutely, yeah, exactly. Is it starting to make more sense? This is real, this is proper chemistry. And thinking about chemistry like this. If you want, I will do an extra video. Maybe next lesson, I will bore you about... Do you want to know where electronegativity comes from? Tim, I don't know. I will tell you where electronegativity comes from first principles. No, Andy, it's the opposite. It's the opposite in a way, right? Because we're not accounting for an interaction which is there, and in our model, we're only looking for one. Wicked. Okay, cool. We will leave it there. Right. I will say ta-ta, and I will catch you guys... Differentiation from first principles. Okay, we'll leave it there, and I'll catch you guys next Wednesday. Monday's being rescheduled because I can't make Monday, so that's being rescheduled to Saturday. You'll get an email about it. And Wednesday normal. Thursday I'll do something like this if you're cool with that. Do we want another Thursday lesson? Let me know before you all disappear. Okay. Saturday 9. Not this Saturday, the following Saturday, 31st or something like that. Not this Saturday, the one after, Andy. Early bird catches the worm. Yep, 9 a.m. 9 p.m. No. 9 a.m. We did loads of business. You just came late. Nafisa, no. It's 9 a.m. Right. And on that note, I will see you later. Ta-ta.